All right, hey, good to see you. Good to see you. Good to see you here. We are going to do Unit 2, Homework 1, questions 4 through 10. All right, so let's do this. These are those projectile launch problems. Let's go. All right, I like to put this little template on my paper, and off we're going to go. Let's do these. Label the launch speed. So this is question 4. There's my launch speed. There's my angle. Draw your triangle. Use SOHCAHTOA. Move that over. Yeah, the way I punch that in, I just punch it in. I like to think of that as the speed the thing scoots along at. It's a great way to think of that horizontal velocity. Yeah, I don't know, for at least this kind of calculator, a lot of people ask, there's a little DEG, a little degree. Really, you just kind of click this mode button, this degree mode button, till it is in degrees. There's also, keep in mind, if you're looking at that, there is the VY portion. Just move that over. Once again, I just punch it in. Whenever I use sines, cosines, I like to take a deep breath and just kind of ask myself, is this speed it starts climbing at, how does that compare to that speed it's scooting at? And really, I look at the angle. So at 60, it's above 45. Remember, 45 is kind of our place where it's going to be. Is I still on? All right. Yeah. So 44 is the place where they're, 45 degrees is where they're even. So yeah, so it does make sense it's climbing faster than it scoots above 45 at 60. All right, so step two on these questions is, really, these are on Earth. All right, I know we talked about launching things from the moon, but as long as we're on Earth, we'll do softball, we'll do golf. They practice here on Earth. Use 10. The VY, that climbing speed, is what we put in right here. Now, really what you're doing that when you find time, so that's really what step 2 is find time, solve for t. The way you set up this equation, it's really from the top to the bottom. So when we solve for t, we need to make sure we double it to get total time in the air. All right, yeah, and once again, that's pretty fast, it's pretty fast swing of the bat, pretty fast launch, or swing of the club, I should say. So that, anyway, there's my time, but you want to make sure you double it. So we want to make sure we use total. We used to refer to that as the hang time. So that total, just double it, 7.6. So yes, so once again, when you find the time, keep in mind kind of the technique or the way I'm teaching you to do these. It only gets us halfway. So when we double it, that gives us our total time. And then really step 3 becomes, hopefully pretty simple. Our Vx, keep in mind that is the speed it scoots at. So I can use 22. I'm solving for dx. That's what step 3 is all about. And I want to use the total time. So I get 167.7 meters. All right, and that makes sense. I don't know if you've been out to a golf course. That's a pretty good golf shot. But yeah, I mean, if you're swinging the club really fast, launching it at that angle, to me, it makes sense to have a ball go that far. So that is, in fact, our answer. All right, I'm just going to keep doing these, and maybe it helps. So if you want to watch this in fast motion, I always encourage that. Okay, I'm just going to go right on to number 5. Same kind of deal here on number 5. All right, I kind of like using this almost as a little template for myself. Kind of helps me remember how to do these. Okay, so number 5, looking at that one, I like to label same speed, different angle now. So once I've got, then draw my Vx vector, and draw my Vy vector. Cosine is the adjacent. So I can get an answer there. So we'll play the same game with the sine. So I know it's just me. I kind of like to write them out. Then I get my calculator out. But remember, whenever I get my answer, I do pause. I do take a deep breath just to see if it makes sense. Okay, these do make sense. Once again, when you're at 50, I would expect the Vy to be bigger. I never draw my triangles to scale. Yeah, but just keep in mind that's the speed it scoots at. That's the speed it starts climbing at. Those become the values we need for step 2. All right, so step 2, let's do that. We can use 10. Our climbing speed is what you plug in. That's kind of a simple way to do these. I still, even though I know a lot of you can do it in your head, I still like to write it out. Because remember, and this is kind of what I've started to introduce, our accelerations aren't always just 10. All right, so especially if you're in free fall on another planet or on the moon or something. So yeah, 10's a great number for Ladue High School, for Earth. Keep in mind that's just because we're on Earth. That's really why I'm using 10. That is only halfway, so don't forget that other piece. Get that total, and just double that. That's the number you want to use. Okay, so please use the total time. So yeah, when we get to step 3, I knew that the scooting speed. That is this. Dx is what we're solving for, and the t there. So that's, yeah, and really it's just pretty easy to multiply that across. And that is our answer. Now, does it make sense? And I kind of think about, well, what is number 4? Number 4 actually had 60. It was a little bit tall. Remember, the closer the angle is to 45, the most range, the farther it's going to go. So yeah, so even though it was hit at the same speed, we would kind of expect this 50-degree launch to go a little bit further. All right, cool. So that was number 5. Let's take a look. Let's try 6. All right, same deal, same deal. I just like to label the angle. Same speed again, same speed. I kind of keep having them swing with the same amount of oomph. Okay, so we can do this. There's the X, the Y. I get lazy, I get sloppy drawing those vectors. We kind of get the idea it's supposed to be a triangle. Cosine of the angle. Just moving that over. Punch that in a moment. We'll go ahead and do it. Okay, I can play that same game with the Vy, the sine is opposite. For that launch speed, kind of a shortcut as you watch this happen, that launch speed is always our hypotenuse. Once again, kind of the approach we're taking here, if you just can recognize sine and cosine as a button on the calculator, you'll be in good shape. All right, so I got some answers. And once again, I try to always say, take a deep breath. Does the climbing, so at 40, I'm actually expecting it to scoot a little faster than it climbs. And that's what I see. That does make sense. And really, once again, I never really draw them to scale, but hopefully you can kind of visualize a 40-degree angle. You do get a longer X. Okay, so those numbers become the numbers we need for step 2. We are on Earth still for all of these. So that's why I put in 10 for our free fall acceleration. Your climbing speed is what we substitute in. So it is this kind of getting that habit. You got the vertical component, plug it in. Still kind of do this the long way here. All right, now I always have to kind of remind myself that's only half the journey. So to get myself going up and down, and I guess there's a lot, it's just multiplication. So some people double it at the end, it doesn't really matter when you double it. Just keep in mind that time, to get total time, multiply that by 2. Okay, so I get to step 3. I'm going to plug scooting speed in there. I'm going to plug total time in there. And this will just multiply across. Multiply across. That sounds eerily familiar. Interesting. So that's, Mr. Watterson, that's the same answer you got on number 5. That is true. Number 6 has this answer. Number 5. Number 5 had the same answer. It was a different problem. It was a different angle, but we do predict that they would land in the same place. So 5 and 6 actually had the same answer. All right, let's try. Let's see what happens here on 7. Let's try number 7. Okay, once again, thanks for watching. Maybe this helps you. All right, so what do? I label the angle 30 degrees. So it's getting a little smaller. Still the same Still the same launch speed though. All right, so I can start there. I like to finish off my triangles. So I get lazy. I don't even always touch. They are supposed to touch. I just kind of get lazy. Cosine is adjacent. Move it across. All right, let's see what I get. I'll just punch it in. All right. So, yep, I'd like to remind myself, scoots along. We can use the sine. It's the opposite over hypotenuse. And just punch it in. Now, it should be smaller. It should be smaller. Yeah. So there's the speed it climbs. So that's step one. Step one, draw that triangle. Get Vx, get Vy. Okay, then it's Vy. It's Vy, and we plug in up here. Once again, we're still playing around near Ladue High School. I don't know, what are we? Yeah, I guess we're getting to still golf balls here. I guess Forest Park. A lot of people play golf there. So once again, this climbing speed of 22, just plug it in. It's the easiest way. That does represent that change from the top to the bottom. I don't know, hopefully, yeah, sometimes just watching helps you kind of find these patterns. A lot of times students kind of find their own shortcuts. I encourage that. So total time, since it's symmetrical, total time up and down. It's pretty easy. Okay, so then, then what's next? We got this scooting speed, that's our Vx. We got our time, that's our t. And we're going to solve for d, how far? Yeah, so we can do that. Vx, that, time, all right, multiply it across. It's pretty easy to solve that one. That looks familiar too. All right, that is our answer. Now this is interesting because number 7, that's the same answer as number 4. So there's number 7. Take a look at number 4. Huh. Number 4, number 7, same answer. Number 5, number 6. Same answer. Same answer. So what does that tell us? What is that indicating for us? Well, so let's keep doing these. Number 8. Number 8 was all about, it asked you, what does it mean to compliment? Well, I guess everyone likes compliments. Hey, you look nice today. Complementary angles. That just means they add to 90 degrees. So some examples, 40 and 50 degrees. Those are complements. We looked at launches at 30 and 60. Those are also considered complementary. Here's the whole key. What does that mean? Well, and I don't know, maybe you've played around with like a hose, squirting water. Lots of ways to kind of think of this. But when we did the math, kind of that combination of the scooting speed and climbing speed, what happens is those complementary angles, as long as we have the same launch speed, they give us the same range, we call that. It really kind of comes from the shooting range or the golf range. Really a better way to think, the horizontal distance is the same. So if you launch it at 40, it goes the same distance as if you were to launch it at 50. So as long as you hit it at the same speed, kind of that combination of climbing and shooting speed go the same distance. So really that's the answer. That's really the answer to question 9. Question 9 was, what did you notice? Maybe going through some of those. All right. And then also, I think we kind of talked about this, but what angle? So what angle is going to provide the maximum range? What angle is going to allow us to launch things the furthest? And once again, range is just not up, just across. Well, the angle that provides the most distance, as long as we got that symmetrical aspect to its motion, that best combination of climbing and scooting is 45. Hey, thanks for watching. Maybe this helped you, maybe not. I don't really know. Appreciate your time. That was Unit 2, Homework 1, questions 4 through 10.